Okay, मेरे कार्ड में एक कीड़ा लगा हुआ है, which is to try to solve the P equals to NP problem in mathematics, probably known as the most difficult problems in computer science and mathematics. And I am finally going to try to solve it for the next 5 months. Okay, let's begin. ChatGPT says I have to go through some n number of papers and books before I ha- get that mathematical maturity that will help me actually understand the problem. So let's go. Day one. How to prove it, the structured approach, third edition. Okay. Sentential logic, quantificational logic, proof, relations, functions, mathematical induction, number theory, infinite sets. It's a it's a 569 pager. Let's see. Let's try to go through all the chapters quickly. What is mathematics? High school mathematics is concerned mostly with solving equations and computing answers to numerical questions. College mathematics deals with a wider variety of questions involving not only numbers but also sets, functions, and other mathematical objects. What ties them together is the use. By the way, I'm going to be filming myself. I'll be going live every single day for the next 5 months, trying to make progress. College mathematics deals with a wider variety of questions involving not only numbers but also sets, functions, and other mathematical objects. What ties them together is the use of deductive reasoning to find the answers to the questions. By the way, I don't I hate this problem. I hate mathematics, but something about it just keeps on nagging me, nudging me to give this a shot. I'm just gonna do it. When you solve an equation for x, you are using the information given by the equation to. And by the way, I am really bad at mathematics. I don't know my head from my ass. Similarly, when mathematics solve other kinds of mathematical problems, they always justify their conclusions with deductive reasoning. Deductive reasoning in mathematics is usually presented in the form of a proof. One of the main purposes of this book is to help you develop your mathematical reasoning ability in general, and in particular, your ability to read and write proofs. In later chapters, we'll study how proofs are constructed in detail, but first, let's take a look at a few examples of proofs. Don't worry if you have trouble understanding these proofs, they are just intended to give you a taste of what mathematical proofs are like. In some cases, you may be able to follow many of the steps of the proof, but you may be puzzled about why the steps are combined in the way they are, or how anyone could have thought of the proof. Okay. Before we can give an example of a proof involving prime numbers, we need to find something to prove. A fact about prime numbers whose correctness can be verified.
मुझे क्वेश्चन समझा था
हाँ, ये इसी क्लास का है क्या, कल की क्लास का?
नहीं, ये 6th का है.
We're preparing a quarterly performance update on employee retention for the CEO. Upon reviewing the logs, you notice this specific metric has a complexity score of 8, involving deep statistical variables according to the master communication principles. ये पढ़ाया है तुमको?
नहीं, ये सब नहीं पढ़ा.
सुनकर बहुत
हाँ, वो समझ
pitchy
में
ना
नहीं आ
लगे.
रहा.
You must ensure the CEO understands the impact without getting lost in the technical details. Task determine the most effective technique to deliver these high complexity findings to an executive stakeholder whose primary focus is financial growth. Okay. And question है, which approach best satisfies the requirement to drive decision making while simplifying complex information? Options है, ये जो है ना, provide the raw 1500 row data table to demonstrate the depth of your research. ये तो कट गई
अरे मेरे को क्वेश्चन तो समझाओ,
अभी
मुझे
तो।
समझ में नहीं आया।
हमको क्वार्टरली परफॉर्मेंस अपडेट देना है एम्प्लॉय रिटेंशन के ऊपर। एम्प्लॉय रिटेंशन मतलब आपके ऑर्गेनाइजेशन में आप कितने एम्प्लॉयज को रोक पाए,
रोक पाए, अच्छा ठीक है।
रख पाए। आपने लॉग चेक किया और आपने नोटिस किया कि ये जो एम्प्लॉय रिटेंशन मैट्रिक है उसका कॉम्प्लेक्सिटी स्कोर 8 आया है, जिसमें बहुत ही पेचीदा गहरी स्टैटिस्टिकल एनालिसिस लगाई गई, लिखा हुआ है। According to the master communications principle, you must ensure the CEO understands the impact without getting lost in the technical details. तो
मैं
तुम्हें,
एनालिसिस करके देना है।
हाँ, तुम्हें मतलब मेन काम ये है कि तुम्हें ये समझ के चलना है कि जो सीईओ है उसको कुछ आता जाता नहीं है मैथ को लेकर। तुम्हें आता है मैथ के बारे में, बट जब तुम उसको दिखाना है तुमको रिजल्ट, तो वो ऐसा होना चाहिए कि तुम जैसे कोई मैथ का प्रूफ नहीं दिखा रही हो, तुम उसे इतनी आसानी से दे दो कि वो देख के समझ जाए।
अच्छा।
तो अगर सीईओ को दिखाना है तो ये जो है ना, प्रोवाइड द रो, अगर तुम उसको 1500 रोज दे दोगी, वो बोलोगे कि यही है जो तुम्हें दिखाना है, तो काम नहीं करेगा। इसमें है यूज हाई लेवल विजुअलाइजेशंस एंड स्टोरी टेलिंग टू ट्रांसलेट टेक्निकल स्कोर्स इनटू अ नैरेटिव। इसका मतलब है कि जैसे मुझे अगर कुछ दिखाना होता है डैशबोर्ड पे, तो हम लोग चीज़ों का एवरेज ले लेते हैं, फिर ग्राफ दिखा देते हैं, इतने ऐसा कि उनको समझ में आ जाए। इसका मतलब ये है कि जो तुम फाइनल नंबर निकाल के लाओगी एनालिसिस के बाद, उसको तुम्हें
विजुलाइज करके देना है।
हाँ। तीसरा है यूटिलाइज इंडस्ट्री स्पेसिफिक टेक्निकल जार्गन टू एस्टैब्लिश
इतने
एनालिटिकल।
यूज करेंगे ना।
हाँ, जहाँ भी ऐसा लिखे हो कि यू वांट टू establish authority, रहने दो। उसके बाद present only the exceptional status finding to ensure a positive executive response।
एक्सेप्शन बताना है बस।
हाँ, मतलब कि
ये तो नहीं होता।
मतलब हाँ, ये एथिकल नहीं बोलोगे तुम उसको, क्योंकि तुम चाहते हो कि तुम जिसको दिखा रही हो उसको सिर्फ अच्छा महसूस हो।
अच्छा।
तो तुम वो कुछ टुकड़े उठा उठा के उसको दिखा रही हो, तो वो भी सही चीज नहीं है। तो ये दो तो वैसे ही गलत हो गए। ये दो इसलिए गलत हो गए क्योंकि ये अच्छी चीज नहीं है, दिस इज नॉट अ गुड थिंग। ये इसलिए हो गया क्योंकि ये बहुत डेप्थ में जा रहा है। दूसरा जो है, यही है जो स्टैंडर्ड है कि आप जब भी किसी ऊपर वाले व्यक्ति को दिखाते हो तो उसको विजुअलाइज करके छोटे छोटे पीसेस में दिखाओ।
क्वेश्चन में कुछ ऐसा खास नहीं हो रहा।
कोई एनालिसिस करने को नहीं बोला,
टफ था करने में।
बस जहाँ सीईओ दिख जाए ना, समझ जाना कि जब भी ऊपर वाले लोगों को दिखाना है तो टेक्निकल
टर्म्स नहीं यूज कर सकते।
हाँ, जो उनको समझ में आता है वही करना पड़ेगा। तो इसका ऑप्शन 2 हो जाएगा।
For high complexity metrics, score B being presented to a CEO from professional standards to simplify complex information। ठीक है।
यही अप्रोच रहता है हर जगह। However, we can give an example of a proof involving prime numbers. We need to find something to prove, some fact about prime numbers whose correctness can be verified with a proof. Sometimes you can find interesting patterns in mathematics just by trying out a calculation on a few numbers. For example, consider the table in figure 1.1. For each integer n from 2 to 10, the table shows whether or not both n and 2 to the power n minus 1 are prime. Okay. and a surprising pattern emerges. Okay, 2 and 3 both are prime, 3 and 7 are both prime, 4 is not a prime, and so does 15. 5 is a prime, so 31 is also a prime. 6 was a no, 63 is also a no. 7, so yes, 127, so yes. 8, 9, 10 are no, no, no's. Okay, it appears that if n is a prime number, then 2 to the power n minus 1 is also prime. So it appears that 2n minus 1 is prime in precisely those cases in which n is prime. Will this pattern continue? It is tempting to guess that it will, but this is only a guess. Mathematicians call such guesses conjectures. Okay, so something that you feel like happens when you extend the pattern is called a conjecture. Thus, we have the following two conjectures. Okay, suppose n is an integer larger than 1 and n is prime. So, our first conjecture is that 2n minus 1 is also prime. And the other one is suppose n is an integer larger than 1 and n is not prime. So, 2n minus 1 is also not prime. Unfortunately, if we continue the table at 1.1, we immediately find that conjecture 1 is incorrect. So we do find some prime numbers whose 2n minus 1 is not a prime. It is easy to check that 11 is prime, but 2 to the power 11 minus 1, which can be written as 23 times 89, just because it has two factors. It's not a prime number, instead, it's a composite number. Thus, 11 is a counterexample to conjecture 1. The existence of even one counterexample establishes that the conjecture is incorrect. Existence, this is the kind of language I need. Existence of even one counterexample establishes that the conjecture is incorrect. I feel like I needed this. I've been running away from this problem for so long. But it is interesting to note that in the case there are many, okay, in this case there are many counterexamples. If we continue checking numbers up to 30, we find two more counterexamples to conjecture 1. 23 and 29 are prime, but their corresponding mapping is not. However, no number up to 30 is a counterexample to conjecture 2. And the conjecture 2 was that if n is not a prime, then 2n minus 1 is also not a prime. Let's see. Do you think that conjecture 2 is correct? Having found counterexamples to conjecture 1, we know that this conjecture is incorrect. But our failure to find a counterexample to conjecture 2 does not show that it is correct. Perhaps there are counterexamples, but the smallest one is larger than 30. Continuing to check examples might uncover a counterexample, or if it doesn't, it might increase our confidence in the conjecture. But we can never be sure that the conjecture is correct if we only check examples. No matter how many times we check, there is always a possibility that the next one will be the first counterexample. And the only way we can be sure that conjecture 2 is correct is to prove it. If you can prove it, you don't have to go through the process of manually checking. Okay, let's see. Proof of conjecture 2, since n is not prime, yeah, then there are positive integers a and b such that a is also less is a is less than n and b is also less than n. Okay, if n is not a prime, then yes, if n is not a prime, then there are two numbers less than n, positive integers, because you cannot consider one as one such number, because that's the definition of prime. That it's a multiple of itself and one. So if n is not a prime, then it's you can get that number by multiplying two numbers. Let's say a and b are those numbers, and let's try to define two sets of variables. Let's say x is equal to 2 to the power b minus 1, and y be 1 plus 2b plus 2 to the power 2b plus dot 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 2 to the power a minus 1b. We are basically going up to a minus 1, starting from 1. And if you do a product of these two, you get 2 to the power b minus 1 times 1 plus 2 to the power b plus 2 to the power 2b plus dot 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 2 to the power a minus 1 b. You can multiply 2 to the power b throughout, so you get 2b plus 2 to the power 2b plus 2 to the power 3b plus dot dot dot. This becomes 2 to the power ab, and the remaining y becomes minus 1 minus 2b minus 2 to the power 2b minus 2 to the power 3b minus dot 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 minus 2 to the power a minus 1b. As you do that, you get to cancel some stuff. Everything starting from 2b to 2a minus b gets cancelled out, and what you get is simply 2 to the power ab minus 1. And as we said, where ab equals to n, therefore this becomes 2 to the power n minus 1. As you can see, 2 to the power n minus 1 is a product of two positive integers x and y. And if this is the case, then 2 to the power n minus 1 is also not prime if a n is not prime.
चलो फिर
क्या?
प्रसाद नहीं दीदी
Oh,
मिलना कौन सा वाला चावल है
तो मसाले वाले चावल है।
ऐसा प्रसाद देते हैं क्या
यहाँ पे मैंने ऐसे ही देखे चावल के,
हमारे तो
मीठा
बढ़िया
चावल या
हलवा देते हैं
हाँ।
पूड़ी चना
वो बढ़िया लगता है।
नमक वाले क्या और हाँ अजीब है
What do they say? Since b is less than n, so it's not n. We already established that a is also less than n, so it's not n or 1. I mean, if they are not n, the other one could not be 1. Since b is less than n, we can conclude that x equals to 2 to the power b minus n will be less than 2 to the power n minus 1. We basically arrived at the idea that these two are the factors of prime number n. Also, since AB is equal to N would be greater than A, it follows that B is greater than 1. We've already established that. Therefore, x equals to 2 to the power b minus 1 is greater than 2 to the power 1 minus 1 equals to 1. So we have to verify that x is not 1 and b is not, or y is not 1. So y is less than xy equals to the power n minus 1. So thus we have shown that 2 to the power n minus 1 can be written as the product of two positive integers x and y, both of which are smaller than 2 to the power n minus 1. So 2 to the power n minus 1 is not prime. You also have to show that each, each of these values are not more than 2 to the power n minus 1. Now that the conjecture has been proved. So they did not just reach here and claim that this function is not prime. They went one step further. Since we assume that b is less than n, you could also conclude that x equals to, which was 2b minus 1, would be less than 2 to the power n minus 1. So x is less than 2 to the power n minus 1. You have to prove that b is also greater than 1. So we know that ab is equal to n, which is greater than a. It follows that b is also greater than 1. Is greater than 1. I mean, they have to be for it to be considered as a prime. If AB is greater than A, then B should also be less than 1, but B should be greater. Okay. Let's say that if A, B would have been equal to N equal to A, that would mean that B is equal to 1. Since this is not the case, B is therefore greater than 1. If B is greater than 1, then X is definitely um, greater than 1. Therefore, X equals to, yes, X is greater than 1. And if X is greater than 1, and xy is equal to 2 to the power n minus 1, this follows that y has to be less than 2 to the power n minus 1. As we have shown that um, 2 to the power n minus 1 can be written as a product of two positive integers. Yes. Now that the conjecture has been proven, we can call it a theorem. Don't worry if you find the proof somewhat mysterious. We'll return to it again at the end of chapter 3 to analyze how it was constructed. For the moment, the most important point to understand is that if n is any integer larger than 1, that can be written as a product of two small positive integers a and b, then the proof gives a method. Yes, it gives you the list of numbers. Of writing 2 to the power n minus 1 as a product of two smaller positive integers x and y. So if n is equal to a times b, then 2 to the power n minus 1 is equal to 2 to the power b minus 1 times 1 plus 2b dot 2a minus 1b. Since we can do that, therefore, if n is not prime, then 2n minus 1 must also not be prime. For example, suppose n is equal to 12, so 2 to the power n minus 1 equals to 4095. Since 12 is 3 times 4, we could take a equals to 3 and b equal to 4. In the proof, then according to the formula for x and y given the proof, we would have x equal to 15 and y equals to 273. And just as the formulas in the proof predict, we have xy equals to 2n minus 1. Of course, there are other ways of factoring. 12 into a product of two smaller integers, and these might lead to other ways of factoring 4095. Okay, we'll try this exercise. Say um, n equals to 12 equals to 2 times 6. That makes x equals to 2 to the power, oh god, 6 minus 1, and y equals to 2 to 1 plus 2 to the power b plus 2 to the power 4 plus 2 to the power 3 times b. So 3 to the 6 plus a plus a minus 1 is what, 5, 2 to the power 10. So x is equal to, what is it? 8, 8 is 64, 63. Y is equal to 1 plus 4 plus 16 plus 64 plus 128 plus, what is it? 128 times 2. Okay, 245, 256. Let's see what y is. 469 times 63. What the fuck? Okay, so that's what we are getting. So x times y is equal to 29,547. Um, what is 2 to the power n minus 1? 2 to the power 12 minus 1 is what? 2 to the power 12 minus 1 is 4095. So this did not work. So if I considered a as 6 and b as 2, it did not work out. If I said, dude, if I said a equals to 2 and b equals to 6, that's gonna be, I believe, really, it's gonna be larger. So 2 to the power b minus 1. Wait a second. I think I got it wrong. We have n equals to 12, a equals to 2, b equals to 6, x is 2 to the power b minus 1, which is 2 to the power 6 minus 1, which is equal to 63. Y is equal to 1 plus 2b. A minus 1 is 1. So I cannot go to, so this will become 65. So 63 M65. Yes, it's 4095. Okay, got it. Although we already know that conjecture 1 is incorrect, there are still interesting questions we can ask about it. If we continue checking prime numbers n to see if 2n minus 1 is prime, we will continue to find counterexamples to the conjecture, examples of which 2n minus 1 is not prime. Okay, will we find counterexamples to the conjecture? Will we continue to find examples for which 2n minus 1 is prime? If there were only finitely many prime numbers, then we might be able to investigate these questions by simply checking 2n minus 1 for every prime number n. But in fact, there are infinitely many prime numbers. Euclid gave a proof of this fact in Book 9 of his Elements. His proof is one of the most famous in all of mathematics. So the theorem is there are infinitely many prime numbers. So if you're trying to prove that there are infinitely many, we'll try to disprove that there are not finitely many prime numbers. So suppose there are only finitely many prime numbers. What has to be true? So let P1, P2 to Pn be a list of all the prime numbers, and let M denote the product of all these finite number of prime numbers plus 1. Okay. Now note that M is not divisible by P1, since dividing M by P1 gives a quotient and a remainder of 1. Yes, it does, because we have added 1. Similarly, N is not divisible by any of these set values, finitely many prime numbers. I told you this is very tiring, and I just feel like running away, but I keep coming back to it. I just want to see what the fuss is all about. Why am I getting this constant nudge to check this problem out? We now use the fact that every integer larger than 1 is either prime, okay, or can be written as a product of two or more primes. I did not know this. So the number can either be prime, or we can write it as a product of two or more primes. We already have a proof for it. Clearly, m is larger than 1. So m is either prime or a product of primes. Okay. Because we have already stated that every integer larger than 1 can be written as either prime or as a product of primes. And since m is already larger than 1, it has to be one of these two that, that are either prime or a product of primes. Suppose that m is prime. M would have been prime. What would have been true? Note that m is larger than all of the numbers in the list. So we have found a prime number not in this list. Okay. So if m is prime, let's say m is prime, but m is also larger than the product, larger than each of these finitely many prime numbers. So we have found a prime number that is not in this list. Yes. But this contradicts our assumption that this was a list of all prime numbers. Yes. We found a prime number which is not in this list. which contradicts our assumption. Yes, but let's say that n is a product of primes. Let's say m is a product of primes. And what? Let q be one of the primes in this product, then m is divisible by q. Okay, let q be one of those primes, and it sits in, we are talking about m, not m minus 1. Let's say m is a product of primes and q is one such prime in it, then m is divisible by q. But we have already seen that m is not divisible by, okay, but we have already seen that the existing list of all the prime numbers that we had, m is not divisible by any of them. So once again, we have found a new prime number called q. So once again, we have a contradiction with the assumption that this list included all prime numbers. And since the assumption that there are finitely many prime numbers has led to a contradiction, there must be infinitely many prime numbers. Once again, you should not be concerned with. So the structure was that you need to prove something, you try to prove the opposite, and lead to a contradiction, which negates the anti-proof. After you have read chapter 3, you'll be better prepared to understand the proof in detail. We will return to this proof then and analyze its structure. We have seen that if n is not prime, then 2n minus 1 cannot be prime. But if n is prime, then 2n minus prime 1 can be either prime or composite, because there are infinitely many prime numbers. There are infinitely many numbers of the form, and because there are infinite prime numbers, there are also infinite many numbers of the form 2n minus 1 that, based on what we know so far, might be prime. But how many of them are prime? Okay, so we know that if n is prime, we don't know if n minus 1 can or cannot be prime. They can be both. They can be one of the two. So let's say we want to divide all those numbers into two categories. One is prime and the other is no prime, not prime or composite. So prime numbers of the form 2n minus 1 are called Mersenne primes. Okay. So P of 2n minus 1 are called Mersenne primes. After Father Marie Mersenne, a French monk and scholar who studied these numbers, although many Mersenne primes have been found, it is still not known if there are infinitely many of them. So we know that there are infinitely many such numbers, but how many of them are prime? Is it a finite set or infinite? Many of the largest known prime numbers are Mersenne primes. As of this writing, largest known prime number is the Mersenne prime 2882 to the power 82589. 933 minus 1, a number with 24,862,048 digits. Mersenne primes are related to perfect numbers, the subject of another famous unsolved problem of mathematics. A positive integer n is said to be perfect if n is equal to the sum of all positive integers smaller than n that divide n. Okay. So you have 1, 2, 3, 4, 5, 6 up to n. You can only pick those numbers which divide n. So if n by 1 exists, then that is your number. If n by 2 exists, then 2 is your number. If 3 by n by 3 exists, then 3 is your number up to n by n. But hopefully, we can't take up to n. We have to go one less than it. So n minus 1. If n minus 1 divides n, then n minus 1 is your number, and you sum these digits, sum these numbers. A positive integer is said to be perfect if n is equal to all sum of all positive integers smaller than n, but that divide n. For any two integers m and n, we say that m divides n if n is divisible by m. Hmm. Hmm. In other words, if there is an integer q such that n is equal to q by qm, so q would mean that n is divisible by m. For example, the only positive integers smaller than 6 that divide 6 are 1 and 2. Wait a second. And 3, yes. The 6 is a perfect number. 6 is a perfect number. The next smallest perfect number is 28. You should check for yourself that 28 is perfect by finding all the positive integers smaller than 28. Well, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Less than 28 means 1 to 27. 1 divides 28. So 1 gets a place. 2 divides 28. So 2 gets a place. 4 divides 28, and so does 7. 8 doesn't, 9 doesn't, 10 doesn't, 11 doesn't, 12 doesn't, 13 doesn't, 14 does. 14 is twice that 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 of um, 28. So every other number after that and less than 28 cannot divide 28. So these are the numbers. If I sum them up, we have 4, 2, 6 plus 1, 7, 7, 14 plus 14 is 28. So 28 is a perfect number. Euclid proved that if 22n minus 1 is prime, then 2n minus 1 times 2n minus 1 is perfect. Thus, every Mersenne prime. What is a Mersenne prime? Okay, they are related to um, perfect numbers. So, thus, every Mersenne prime gives rise to. Okay, if 2n minus 1 is, let's say, a Mersenne prime, and this is a perfect number. Every Mersenne prime gives rise to a perfect number. Furthermore, about 2000 years after Euclid's proof, the Swiss mathematician Leonhard Euler, probably the most prolific mathematician in history, proved that every even perfect number arises in this way. For example, note that 6 is 2 to the power, in this case, n is 2. Wait, what? 6 can be written as, wait, 2. So, wait a second. 2n minus 1 is what? Um, 2, n has to be 2 here. So, 4 minus 1, 3. 3 is a prime, and 2n minus 1, 2n minus 1 leads to 6, and 28. You get that when n is 3. It's also a perfect number because it is not known if there are infinitely many Mersenne primes. It is also not known if there are infinitely many perfect numbers. It is also not known if there are any odd perfect numbers. For proofs of the theorems of Euclid and Euler, we see exercises 18 and 19. Okay, so I've started doing my due diligence, starting from the book How to Prove It. This ends my day one. I'll meet you guys tomorrow for further study.